Good morning and welcome to this next lecture on sound and structural vibration. We ended up with this picture in the last class, okay, a schematic of the coupled waves where I showed you the light dotted lines as the uncoupled solutions and the dark black lines as the coupled solutions, and the nomenclature I was going to use. Okay. Now it is time to start finding the mathematical solution from the dispersion equation. But before we do that, let me just show you what I mean by the rigid duct cut-ons. Okay. So we have this duct, 2D duct, okay, and now top and bottom are rigid, lower plate and upper plate are rigid, is rigid. Okay. So what is the plane wave? The plane wave looks like this. This is a plane wave. It is plane. Okay. On the wave front, parameters do not change and it propagates. This is omega by c. Okay. Now what is the next cut-on, n equal to 1 cut-on? It looks like this in terms of pressure. Okay. It looks like this. This is the pressure wave front. Here you have del p del y, which is particle velocity in the y direction or proportional to the particle velocity in y direction is 0. Here also del p del y is 0, proportional to particle velocity equal to 0. So this is the n equal to 1 cut-on. It looks like this. Next, the n equal to 2 cut-on, it looks like this. It's here, it goes like this and it comes back. Okay. So here again del p del y or Vy is 0. Here again del p del y or Vy is 0, and it has a higher deformation profile and so forth. So these are the cut-ons and they will propagate. Okay. If they satisfy the omega condition, they will propagate. Now as I said, let us start deriving, okay, the solutions. So let me have the non-dimensional coupled dispersion equation. Is given by xi to the power 4 by omega square minus 1 into lambda square root of omega square minus xi square into tan of lambda square root of omega square minus xi square plus epsilon equal to 0. So we have to solve this. Okay. So we are going to use the asymptotic method or the perturbation method, and we have seen it before in the classical problem. What we are going to do is that every solution is perturbed by a small quantity. And how do we give the small quantity? So first let us say I am going to look at the perturbed or coupled, both are equal now, flexural wave. Perturbed flexural wave. What was the unperturbed flexural wave or uncoupled flexural wave was given by this. So the coupled value, okay, is going to be omega to the power half plus A constant into epsilon. It's like a Taylor series. Okay. So, this is a small quantity, then order epsilon quantity. Okay, that is the language of asymptotics. It is an order epsilon quantity. This total term is an order epsilon quantity. A1 is an order 1 quantity. A1 is an order 1 quantity. Okay. Now, if we substitute this into this equation, so let us give this, we will call this 1 and we will call this 2. So, if I substitute 2 into 1, what do we get? Okay, we get omega to the power half plus A1 epsilon whole thing to the power 4th divided by omega square minus 1. That is the first term. That is the first term. So, what to do with this? Let us look at this. Okay, we get, I will do a square first. So, I will get omega plus twice A1 epsilon omega to the power half plus A1 square epsilon square. This is the square of this quantity. Next, I need further square divided by omega square minus 1. Okay. So, let us look at that also. I mean, intuitively we can do it, but let us look at that. So, I have omega square plus 4 A1 square epsilon square omega plus A1 4 epsilon 4 plus these two together 4 A1 epsilon omega to the power 3 halves plus twice omega A1 square epsilon square plus 4 times A1 cube epsilon cube omega to the power half. This entity divided by omega square and minus 1 outside. Now, I said epsilon is a small quantity. Okay. If epsilon is a small quantity, our understanding is that epsilon square is a much smaller quantity and epsilon cube is a further smaller quantity. Okay. The powers will reduce in magnitude. So, let us look at the epsilon order. So, this is the order 1 term, that means no epsilon in it. This is the order 1 term. Let us take red. This is the order 1 term. And the ones this with only 1 epsilon are over here. This is the only term with 1 epsilon. Okay. And the one is with epsilon square. This is the term with epsilon square. It is a smaller quantity. This is the term with epsilon square, also the same quantity. This is the only term with cubic in epsilon. That is a further small quantity. And this is the only term with 4th power, the last quantity. So, we will ignore, we will neglect the ones which are higher than epsilon. Okay. So, we will keep omega square plus 4 A1 epsilon omega to power 3 by 2 and divided by omega square. So, this turns out to be what? I get 1, okay, plus 4 A1 epsilon by omega to the power half minus 1. Okay, this minus 1, which is equal to 4 A1 epsilon by omega to the power half. So, this first term is what we have found using this substitution. We have the other terms also to take care. Okay, so what to do? Let's see. So I have the second term here. Let me write xi to be written as omega to the power half plus a1 epsilon, and the term is lambda square root of omega square minus xi square. Okay, so this xi gets substituted in here in this form. So if we do that, I get lambda square root of omega square minus xi square is omega plus twice a1 epsilon omega to the power half plus a1 square epsilon square. Okay. So again there is order 1 quantities, okay, and there are order epsilon quantities. So let us keep till order epsilon quantities. So what do we get? We get lambda square root of omega square minus omega minus twice a1 epsilon omega to the power of half. Okay. Now because this is a first time or this is quite new, I will do it here. So suppose this is a, I will call this some psi, okay, and psi is an order 1 quantity. Let me call this psi square. Psi square is an order 1 quantity. So what I will do, I will take this lambda, take psi square outside as psi, okay, that means I am dividing inside by psi square. So I get 1 over here minus twice a1 epsilon omega to the power half by psi square. Okay. So this is a small quantity, that is our assumption because of epsilon. Okay, this is smaller than this. So if I do a binomial expansion of this, I get lambda psi and 1 minus a1 epsilon omega to the power half by psi square. So I get a half. I get a half in front which cancel with 2. This is what happens, right? Root of 1 minus epsilon is 1 minus epsilon by 2. That is what I have done. Okay, so this term here with this substitution has ended up like this. Okay, so if I want, what do I have? Let us see, just 1 second here. Okay, so this okay, so this was the first term. Just want to remember 4 a1 epsilon by omega to the power half. So I have 4 a1 epsilon by omega to the power half from the first, and from the second I get some lambda psi 1 minus a1 epsilon omega half by psi square. We should remember what psi is, okay. This thing we call psi square, so we should not forget. there is one more tan term. Okay, so one more tan term. So what happens there? We have one more tan term we have, which is tan of lambda square root of omega square minus xi square. Okay. Now we have done lambda omega square minus xi square, so we should not have to do anything here. So it will look like tan lambda psi into 1 minus a1 epsilon omega to the power half by psi square. So in totality now, how does it look like? The first term 4 a1 epsilon by omega to the power half into lambda psi, okay, lambda psi into 1 minus a1 epsilon omega to the power half by psi square into tan of lambda psi 1 minus a1 epsilon omega to the power half by psi square plus epsilon equal to 0. What's the whole idea? We should not forget in the mess. Idea is to figure out A1, which gives me the correction on the flexural wave number, which was omega to the power half. We should not forget that. So out of this, my question is, what is A1? Okay. Now I will pull out first the coefficient of epsilon in this. Okay, if I do that, so this is a total tan term. This is a total tan term with epsilon inside it. Okay, we can't touch it anyway. But here I have epsilon multiplied with 1 and lambda psi, which will be epsilon order quantity. Then here I have epsilon multiplied by epsilon and other things. So this is an epsilon square quantity. So this can be neglected. Epsilon square quantity I am going to neglect. So what am I going to get here? As a coefficient of epsilon and including this epsilon, I will get 4 a1 by omega to the power half into lambda into psi. Psi is square root of omega square minus omega into this tan quantity, lambda into psi into 1 actually I can do something different. Okay, so let's do this, let's do one more, let's just do one thing here. I have a tan, okay, then I have a lambda square root of omega square minus xi square, and xi square I have given it here, xi square already, okay, minus omega plus twice a1 epsilon omega to the power half plus a1 square epsilon square. Now because it's inside the tan, I cannot separate it out algebraically like this. So I will take the dominant terms. So epsilon is a small term compared to omega or omega square. Epsilon square is a further small term. So I will just take it as tan lambda square root of omega square minus omega. So I apologize, I will take this out. Okay, I will take this out. I'll take this out here, and in black write it as lambda square root of omega square minus omega. Okay, and so here tan lambda square root of omega square minus omega, which is what happened here. Okay, that's the same thing that happened here. I just showed you how its second epsilon comes and which is neglected because I get epsilon square. I get epsilon square over here. Okay, otherwise I have square root of omega square minus omega right here. Okay, so plus 1. So the coefficient of omega epsilon now must be set to 0. So this thing must be set to 0. We set it to 0, I will find my A1. Okay. So let us see if I can 4A1 by omega to the power half. Okay, let us see. 4A1 by omega to the power half. So I have 4A1 by omega to the power half lambda square root of omega square minus omega into tan lambda square root of omega square minus omega plus 1 equal to 0. Okay, so we have balanced the equation at order epsilon. We have balanced that equation. Okay, so then what happens? My A1 can be found out. A1 now is equal to, taking the whole thing to the other side, I get cot lambda square root of omega square minus omega. Okay, then I get a minus because this thing has gone to the other side. I get a minus, and this should be omega to the power half. Sorry, this should be omega to the power half. And just check. Yeah. Okay, so this omega to the power half goes on top, and I get a 4th in the denominator, 4 in the denominator, and I get lambda square root of omega square minus omega. Okay, so what is the total solution, perturbed solution now? Xi, original value half, A1 is minus omega to the power half by 4, okay, cot of lambda square root of omega square minus omega by lambda square root of omega square minus omega. Cot is an oscillatory function, okay, caused by sine. Now if omega is less than 1, then between omega square and omega square is less than omega. So we have to get into cot hyperbolic. Okay, so for omega less than 1, take my answer. Xi looks like omega to the power half, okay, with a change of sign. I'm sorry, epsilon has to be there, big epsilon, okay, plus epsilon by 4 omega to the power half cot hyperbolic square root of omega minus omega square by, I think it was a lambda cot hyperbolic lambda, and then lambda square root of omega minus omega square. The sign is switched, please note. Okay, the sign is switched. Okay, and that's below omega less than 1. So this thing is a positive. This thing is a positive number. Okay, this happens to be a positive number. It's a positive number. Whereas for omega greater than 1, we still have this term over here, and it changes sign about a certain frequency. So let us see that frequency. So let us say so I have cot lambda square root of omega square minus omega, okay, which let us say is 0 at some point. Okay, that means cos is 0 at some point. Cot is cos over sine, the cos is 0 at some point, which means lambda square root of omega square minus omega is sum twice m plus 1 pi by 2 . Okay. Okay. So now so this thing at that omega value, there is an omega value where this term is 0, right, where this term is 0. Okay. So now that means let us look at how cos looks like. Cos starts off here and then it goes like this. Okay. Now what happens is that let us look at this over here. Below that particular frequency, okay, below that particular frequency here, your correction, you are positive. Okay, you are above. Below this frequency where cos goes to 0, you are positive here. Above, you are negative over here. Okay. So if you look at Xi equation, minus omega to the power half by 4th cot lambda square root of this thing by lambda square root of this thing, what happens is that below that frequency this correction is positive, so that means this negative will reduce. Okay. And above that frequency your negative means that negative and this negative will increase. For other locations, the sign of cos in the numerator and the sign of the sine in the denominator both will matter, because it is a cot, which is cos over sine. Okay. So let me quickly plot what we have over here in this picture. Let me plot in red, or let me go back. Okay. So we are looking at perturbations to the flexural wave. Okay. Let me use red this time. So, this is the coincidence frequency. Below coincidence frequency the correction was positive, that means to this flexural wave I will have an increment. So, this will be the coupled flexural wave below coincidence frequency. Above coincidence frequency there are frequencies where COT goes to 0, those are these frequencies. Okay. I will talk more about them, these are the frequencies. So, below you will have a reduced value, above you have an incremented value. Below you will have a reduced value, above you will have an incremented value. So, this portion is the coupled flexural wave. This portion, this little portion is the coupled flexural wave. So, the equation we have derived, the solution we have derived, we did xi is equal to omega to the power half and some correction, okay, epsilon by 4 etc. That is represented pictorially by these red portions I have, okay, these short red portions. Okay. So, that means what? This original flexural wave which I now completely show in red, okay, in localized regions as modified to this. This is the coupled flexure, this is the coupled flexure, this is the coupled flexure, this is the coupled flexure. In next class we will find all the other solutions, the coupled plane wave, the coupled rigid duct cut on N1, N2 etc. We will do that in the next class, okay, coupled plane wave here, do that in the next class. Thanks.